The research I show you today is a multidisciplinary approach of different sciences and the research community reaching from medicine to hygienists and to microbiologists, and also the hydrogeology of karst features has its part in this project. I want to speak a little bit about the importance of karst resources in Austria and show you some pictures of karst landscapes. Why we made these investigations, I will show you, and how we managed the high dynamics in karst springs in quality and quantity, and how we established a multi-purpose system for quality insurance and quality warning for this drinking water supply in Austria at a very important spring source for the Vienna waterworks. In Austria, at about 50% of the people are more or less direct consumers of karst waters, and 20% of the landscape of Austria are karstifiable rocks. So it is also for us very important to deal with this. And the study we have carried out was done in the Hochschwab and Schneeberg area on the border between Styria and Lower Austria. Both these sites, they are separated, are the important sites for Vienna water supply from their karst water resources. That's on the top of the Hochschwab area in wintertime, one impression of this karst area. Here we have a pasture in the middle height of this area at about 1,500 meters above sea level, widely used by tourism, and also, as you see at the second picture here, a manure spreader on work directly in the catchment. The usage for alpine pasture and the pressure from this alpine pasture was one of the reasons of starting our investigations. Some of these pictures, I think you know, they are very similar, showing the pressure we have in this area coming from the ruminants and the cattle, from the wild deer, and also from tourism activities from the humans. And as you know from karst, there is a huge amount of event water passing very fast through these areas and also transporting the pollutants easily to the springs. But we have a base of very stable raw water quality at base flow conditions. That's the reason for the importance of these karst water springs. And the catchments we were investigated were very different in the size, coming from 4 to 70 square kilometers, and all of them are very affected by farming, by pasturing and tourism, as I told you, but also hunting is a very important thing there. We tried to establish a three-step approach to protect this water quality, this raw water quality, this aquifer. The first beginning at the catchment protection and the management of these. In some areas it is very easy because the Vienna waterwork owns a lot of the landscape there and can directly influence the land use in these areas. Not at all areas, but that's important. Then the second step is the optimization of the water abstraction. We have only springs for using. We are not in the situation that pumping wells, but we can manage the abstraction from the springs because they are more than 20 springs used for the Vienna water supply. And the last step then should be a treatment, and this treatment should be as low as possible according to the Water Framework Directive. These pictures you know, on the right side, an alpine spring, one of the most important there is the Kleffer spring at high water conditions. So our hypothesis we had, and we formulated it exactly for going for our ongoing research. Our hypothesis was, where are these fecal pollution we have seen in the springs sometimes, not every time, where are they coming from and how they are coming to the spring, at what time, under what conditions, and that was the situation. To make it very short, hydrogeologists, when you remember tracing test activities, you have an amount of tracer, you put it in, and at the spring you are looking at the amount which is coming out. Easy calculation is the recovery rate. If you have the fecal pollution in the springs, it's not so easy to make the input amount, to calculate the input amount. And normally, standard situation would be mapping of the feces. That's also possible, but we had not the time and not the amount of money to do this, but we had a plan for this. But we had another possibility. At one of these regions, the tourism activity are counted sometimes. Some times of the years, the people are counted going up to the mountain, walking or going with the cableway, and it is also known how many cattle are there, and there are some knowledge about the wild deer. And from this, you can calculate the amount of feces, because the hygienists, they know how many feces every population, every individual is producing if it is healthy. You know it from the deers, you know it from the wild deers, you know it also from the humans, and you know how many feces is in this, how many bacteria are in these feces. I can say to you, from cattle, at about 30 volume% of the feces, of the fresh feces, are bacterial. So we could calculate this, and starting then with our investigations, having an idea from whom these feces were coming. From our calculations, we saw that the red deer, the chamois, the cattle are the most important thing. The tourists are less important because we have a special situation of sewage system there. Up to the mountain huts, to the important mountain huts, and there are not very much, there is a sewage system. Some of them are carried, some of these feces is brought down with the helicopter to the valley. In other areas, there are pipes where the feces is transported. So the amount of feces from the people in the nature is very, very low. And so our thesis was the most of these coliform and colis we could find in the springs were coming from the ruminants. We saw it here. So we want also to quantify this now, as this was our hypothesis, and we did this with special genetic markers, and the results of these investigations showed that we were right with our hypothesis, that it is more visible in the springs, clearly more visible in the springs, that the colis, E. coli, are coming from the ruminants. We had at the background of this investigation also investigations between E. coli and the genetic markers we were looking here. I cannot show everything here. The dynamic of karst springs I have mentioned at the beginning. It's also a problem, common problem everywhere. It differs a little bit or very much between different lithology in the catchment. Here it is shown at the discharge of a limestone karst spring, and you have a great coefficient between low water and high water situation. And this is also the same situation with quality parameters, and we had to deal with this and have an attempt to cover all the range of these parameters in quality. And so we established something what we afterwards called a nested sampling design. We had a base monitoring over the year. We had a high frequency monitoring during the times of intensive groundwater recharge. And in this we put our event investigation, as it was shown here. These three parts of the investigations of sampling. To do this, we had also the necessity to use field laboratory methods, especially here for E. coli counting, because it was not able to transfer all the probes to a special laboratory and to count the E. coli, for instance, as the standard method, as the ISO methods are shown. And this E. coli detection via field methodology was very efficient. The correlation is shown here. So we could establish these field laboratory investigations for our research. The other problem dealing with microbial investigations was the die-off rate of these E. coli. The first time they are no swimmers and they don't like it cold, so in the water they are dying. If you make automatic sampling and you put the samples at spring water temperature, these E. coli are going down, and after 40 days, after storing at temperature of the spring, there are no coli anymore available. So we could correct all the data with the time which had passed till we started with the countings of the E. coli. So we showed by this that it also is possible to make a good automatic event sampling by E. coli investigations, or for E. coli investigations. We established, therefore, a network of communication which is based on satellites, because in our alpine regions we have no communication infrastructure in these areas like mobile phones or something else. These mobile phones are not available in these regions because there is no skiing in the wintertime. Only in these alpine regions there you have a GSM combination. And so we did it with these LEO satellites. They cover all the areas. They can look in every gorge, in every narrow valley. And so we made a networking between the catchment area and the spring. And it was possible for us also to get with this system a status sample before a reference sample before the event really happens and occurs at the spring. That means after triggering by rain in the catchment area, we took the first sample immediately at the spring before some quality parameters or quantity parameters have changed. This is shown here, and this is also shown a very important thing for us. In our work there, we combined these online parameters, here shown as the orange line of the spectral absorption coefficient and this field detection of E. coli. This special absorption coefficient was shown for us that it is more important and more triggered to a surface, more surface related and more triggered to anthropogenic impact, as the turbidity. Turbidity is in our alpine regions also part of the cave systems by itself, and it is moved if the discharge is increasing by increasing pressure, by increasing velocities. Spectral absorption coefficient is directly related to the surface and is a surrogate of anthropogenic and organic things. For this we had special devices for in situ measurements, and as these in situ devices are able to measure every some seconds or minutes as you like it, you have a connection via satellite, for instance, or via cable line. These data are available very fast, immediately. In this time, what you have is to react for a quality surveillance system for drinking water. You have not to wait 18 hours or 24 hours till you have the result from the bacteriological investigations, when you can show that this surrogate is really working for your purpose. And the situation at the beginning was shown, and is shown here on the left side, when we did all the samples, as I have shown you from this basic monitoring. When we correlate the spatial absorption coefficient to the E. coli, there was no correlation during the whole 3 years of our investigations. But when we got down to the event scale, then we have a very, very good correlation, and it is shown at every event which we were investigating. And for this early warning system, to establish it, it was necessary that it was important that this lead time, this lead time here at the left, where the spectral absorption coefficient is increasing, but the E. coli are not increasing at the beginning of the event. That's the basic for this early warning system. This was a thing we had to recover that every spring we were investigating different spring and different events. Everywhere it was seen in this way. We say it is a problem of, or it is a situation of the transfer of bacteria or other compounds, and it is also a problem of the activating of the E. coli from the feces at the surface. So at all, as I said, and so we could establish this spectral absorption coefficient as a proxy parameter. And putting this together, we had again these 3 steps for the maintenance of the water quality. If you have a fecal pollution, we have to look on this, to monitor this at the spring abstraction at this level. Then we have to characterize this fecal pollution, where it is coming from, why it is here, and make, if possible, a management of this pollution, this fecal pollution, for instance, lowering the amount of cattle in the pasture or something else. And at the end, that's the important step now, to have a health-related target. That means the people have to can drink the water and will not be ill. So I say it very easy. And you can calculate the reduction you have to reach during the whole steps from the catchment to the spring water, the reduction of fecal amount and the E. coli consumption of the whole time, so that this health risk assessment is reached. And you have different steps of work and time scales on which you are working. You have the online proxy parameters in a near real time. You have the field testing methods of the standard indicators. You have a catchment device, very important. The one is the source profiling of in the catchment, as I have shown it to you. The second part is there is a survey to the catchments looking to changing of land use, erosion startings or something else in the whole area. The source tracking I have mentioned, that it is quality guided. That means we need this QMR depending on the hydrogeological situations that we are working here. And the last part, not realized yet, is a scenario modeling of these health risk related things to the water quality. And as I've said, we have here all the scales in time which are important for this water quality in Karst springs. As we know and have seen, there are very fast components, and we have also a storage component or the different storage components which responds to a high base flow, that they are long stored in the aquifer, and they have also to be monitored. The next step of our work will be how come these pollutants and the feces and the microbes in the Karst system, and we combine this with erosion ideas and say as long as how long a flow path is on the surface of the Karst system, the chance is higher to get fecal pollution into the Karst systems. And so we try to establish a model to identify the spatial patterns of the surface runoff. This is our approach, that these surface lengths, runoff lengths, are important for the quality of the input to the Karst systems. We established therefore a special catalog for mapping based on hydrogeological mapping facilities. We tried to establish a catalog where on the first side everything can be mapped, and on the other side the results of this mapping can directly be an input to establishing the network and the model by itself. These different reaction of these areas are shown here to these different rainfall events, and you see thunderstorm rainfall events, very high intensity and short duration, gives another pattern of surface runoff as a long duration rainfall, where the wettening of the soil before the event has happened. And that's important that the dynamic changing of the flow length passes can be monitored or can be shown with this model. So, as a synopsis, we can say this monitoring of events is very important because it's a worst case scenario, looking at the worst case of transport in Karst. The second was we could establish field laboratory devices for our investigations. The event monitoring is also a possibility to look to further changes concerning to climate change. All of this event monitoring is necessary, is only possible or very effective if you have it integrated to a sampling system where you have also a basic sampling there. The spectral absorption coefficient could be established as a proxy, and this integrated approach of microbial water resource management at all time scales could be established for the value evolving system of these resources, raw water resources. And the outlook of this modeling should be, after the establishing this surface runoff patterns model, we try to make the first steps to modeling the transport in the Karst system. So thank you very much for your attention.